And so I'm going to be leading us on, I'm going to share my full screen, an exercise looking at how we can implement the lexical functional distinction in SPOT. So in the chat, I think there might have been wrong link. So here's a link to the Google Doc where you can find the exercise that we're going to work through. And so basically what we're going to do is take a look at the double object construction. So this is sentences like, give Junko a book, where you have a verb and then two nouns, a theme and a goal. And so what's interesting about this construction is that, as you can see here in the syntax that we're assuming, in the initial verb phrase where you have the two arguments of the verb actually raises out of this VP up to little VP. And so what you have is this verb phrase whose head is a trace. And so what's interesting then is that you have this verb phrase that only contains the two noun phrases to the exclusion of the verb itself. But if you look across different languages at how they actually prosodically phrase the ditransitive structure, Nick Kalavoda in his dissertation showed that although you get a bunch of different patterns, you never have a pattern where the two nouns are in a single phonological phrase by themselves without the verb. So you can get a pattern like Ewe, where each word is in its own phonological phrase. You can get a pattern like Timwini, where you have the verb and the first noun together to the exclusion of the second noun. You can have a similar pattern like Himatumbi, where this time the verb and the noun are in a phrase together, and then there's another phi that contains that phrase and also has the noun. So you get a recursive phrasing. Or you could have a language like Zulu, where you just put the verb and the two nouns into a single phi phrase. So what's interesting here is that we don't find, as I was saying, any phi that only contains the two nouns. And this is perhaps a little unexpected if we thought that a verb phrase should always get matched. So one way to deal with this is introduced in an analysis of Shitsonga by Selkirk and Lee, where they basically propose introducing the lexical functional distinction into match theory. So kind of taking inspiration from Truckenbrott's lexical category condition, they introduce a match constraint that will ignore a VP because it no longer has a lexical head, but will try to match this little VP because now the lexical head V is adjoined to the head of this phrase. So what we're going to show is how to set up an analysis using SPOT, where we are able to encode this lexical functional distinction into the inputs, such that the constraints know which XPs are functional, which ones are lexical, and can assign violations accordingly. So before I go into defining our gen, are there any questions about the basic problem we're looking at? Or anything I could clarify? Okay, I should also say, please feel free to interrupt me at any time if you have any questions, or if you want me to repeat myself or slow down or anything. Okay, so our gen input is only going to have one structure because we're just looking at this ditransitive syntax here. And so we already saw from Jenny how you can go about inputting manually a structure into SPOT. And so I would encourage you to, on your own computer, follow along and build the trees yourself with us. So there's the interface. I just sent the link in the chat. And so because we already have a structure in mind that we want to build, we're going to use the manual setting instead of the automatic one. And our string of terminals is going to be just verb, noun, noun, because that's all we have in the ditransitive structure. So we just enter that here and then click build syntax. And so what SPOT will give us is this sort of bear tree where we have the three heads, the three different words, and then we have a CP at the top. So we're going to want to add in this additional structure so that we get the syntax that we saw above. So to do that, For example, if we wanted to make noun phrases for each of the nouns, you would click on the noun here, and then you click add mother, and now it creates an XP that just contains this noun. And now it's not necessary to change the label of this to NP, but just to make it clear how this matches the syntax we saw above, I'm going to change that label because it makes it a little more transparent for us as we work through this. Okay, and then we can do the same thing for the other noun, where you click on this noun, so it's the only thing highlighted, click add mother, and then again, we can change the name to NP. As you can see here, this is the target structure we're trying to build in Spot. So next, we know that these two noun phrases are in that verb phrase that the verb has already left. So we can build this verb phrase by clicking on both of the noun phrase nodes. So you can highlight both of them. And again, just adding mother, we'll label this VP. And now this is where Spot is really useful because while these phrases we labeled XP, in this case, this VP is now considered a functional phrase because once the verb has left, it only has a trace in its head. It no longer has the lexical word. And so we're going to let Spot know this is a functional phrase by adding a comma, a space, and the word func. So this is really important. This means that later on, when we tell Spot to make a match constraint that only tries to match lexical phrases, that match constraint will ignore this VP because it has this special label. The last thing then is, even though this top node came in as a complementizer phrase, we're actually going to change this also to an XP because it's a little VP. And we're going to want this to be matched as a syntactic phrase to a phonological phrase. So we just change the category there. So once we have this, you just click done, add trees to analysis, and you'll get a message saying the trees in this analysis are up to date. And that tells us Spot is ready with the inputs. So again, I'll just take a brief pause there and ask if there are any questions or if you had any trouble building this tree, or if I should slow down a little bit so you have time to enter the input. Okay, so now that we have our input, another way of thinking about the way that this tree structure we just built in Spot, another way of representing it is as bracket notation, where we have these three lexical phrases and then a functional phrase in the middle. So as we saw in Jenny's earlier talk, after you come up with your input, the next step is to come up with your output. And so we're going to go with a fairly simple gen. So we're going to allow for prosodic recursion. As we saw in the typology above, at least one of those languages had recursive phi, so we want to include that in our outputs. And then we're also going to make it so that the root of the tree is an intonational phrase. All children of the intonational phrase are phis. So for the intermediate nodes, we say only phi is checked. And then every head is mapped to a prosodic word in the prosodic tree. Another way of saying that is that all the prosodic terminals are words. So the verb and the two nouns will each separately be mapped to a prosodic word. We're not going to allow movement, so we want everything to remain in the same order. And the only other thing is that we're going to say no level skipping, or in other words, we're going to enforce exhaustivity. So what this means is we can't have an iota that immediately dominates a word. There has to be a phi in between. The condition here is fairly simple. We just need to check this exhaustivity box. And then we'll stick with the default settings for everything else. So if I could have any thumbs up again, if everyone is ready for that. And also if there are any questions, feel free to ask. Okay, great. I see some thumbs up. Okay, so then here our inputs aren't too complicated. or sorry, the outputs weren't too complicated. So now we can move on to talking about con. So what constraints do we want to put into our analysis? And so the analysis that we're doing is based on what Nick Halvoda did in his dissertation, which itself was inspired by Lee and Selkirk, 2017. So we're going to start by looking at our match constraints. And so we're going to have 3 different kinds of match constraints in our system. So the first one is going to be a general match XP, and this is going to try to map every single XP onto a phi. And it doesn't care if that XP is functional or lexical, as long as it's a phrase, it's going to be mapped to a phi. So to include that, we can click match syntax to prosody. Syntax to prosody is how it's represented on the interface, but that's just another way of saying, as we have in the handout, you're matching an XP to a phi. So as you'll see here, just as a note, we're going to use XP because we're concerned with the phrase level. But depending on what data you're working with, what you're interested in analyzing, you could also do it for CP, so like a match clause, or for heads, so like match word. So there are a lot of options if you want to experiment with different types of match constraints. You'll also see that there's an option to make it so that we only look at lexical phrases. But for now, we're not going to check that because we're going to create a custom match constraint instead to look at lexical XPs. Because following Halvoda's analysis, we're going to include both the general match, which is this constraint, as well as the lexical match. Okay, so then here's where it gets interesting. We get to click on show more. And to create match a lexical phrase to a phi, we're going to go to custom match syntax to prosody. So this is custom because there are a lot of different options here for what exactly we want to get matched. As I mentioned before, if you just click lexical, that means that only those phrases that are lexical will be assessed by this constraint. In other words, this constraint is defined in spot so that it ignores those XPs that we marked with comma func in our inputs. Sorry, it's a little slow scrolling. So again, this was the syntax to prosody version where we're saying take a lexical XP and map it onto phi. But we also want to have one that requires every phi to have a corresponding lexical phrase in the input. So for that, we need our prosody to syntax constraint. So again, we'll click on custom match, but this time for prosody to syntax. And we're going to leave phi checked because that's the relevant prosodic category for our analysis. And again, we're going to check that we want the syntactic phrases to be lexical. So we don't care about having phis that have functional phrase correspondence. We only care about the lexical ones. Okay, so again, if I could get thumbs up for the match constraints. And again, if you have any questions.
Nick, if it's possible, do you mind scrolling up and showing the first constraint?
Oh, yes, definitely. Yeah, so the first constraint was this match syntax to prosody.
Excellent, thank you.
Yeah, I'm gonna make this screen a little bit bigger. It might cover up the exercise page, but I'll just be switching back and forth. So yeah, we have this match syntax to prosody where we only want to check off XP. So that'll match all XPs. And then we have our 2 custom constraints where we want it to be XP lexical and phi lexical. Okay, sorry, I missed if there were thumbs up before, but okay, I see a few now. Okay, great. So those are our mapping constraints, so ones that will tell us how syntax and prosody should correspond to each other. But in addition, we have our markedness constraints. So here we have just a few standard constraints that we'll be using. So the first two are our binarity constraints. So if we scroll down past these match constraints and past the alignment constraints, we'll get to our markedness constraints. So here there's a tab binarity, and we click on that. And so specifically, the constraints that we're going to use in our analysis are those that count branches. So binarity minimum will say that every phi should be at least binary branching. So it'll assign a violation to every candidate that has a unary branching structure. So that would be like if you had a phi that only dominated a single word, that's unary branching, this will assign a violation to that candidate. But if you have a phi that then dominates two words, that'll be binary branching, and that won't be assigned a violation. So to incorporate this, all we have to do is click on bin min branches. And by default, it's already counting at the phi level. The other one is sort of the complement of that. This is bin max branches. And so this says that every phi should have at most 2 branches. So this will assign a violation, for example, if you have a phi that dominates 3 words directly, it'll assign a violation to that type of structure. So again, we'll just click bin max branches, and phi is selected by default. Okay, are we all on the same page for this part? Thumbs up. Okay, great. Then the last constraint we have is strong start. And this is a constraint that will assign a violation for every phi whose initial daughter is a word and whose pen initial daughter is phi. So basically, this will penalize structures in which at the left edge of phi, you have a word and its sister is a phi, because it doesn't like starting with a weak category like word and then going up one level on the hierarchy to phi. So basically it's saying, don't have a word followed by a phi. So this has been used in a lot of different analyses, like the Selkirk and Lee-Tsonga analysis. And so this is a constraint on sisterhood because it tells us what order we can have our prosodic constituents in. So for this, we're going to click on strong start local by child category. And so in this case, we're going to uncheck word, and we're going to say that it can count all categories. But really all it's going to do is say you can't have a word followed by a phi. Okay, so those are the rest of our markedness constraints. I guess that was only one more, but are we ready to download our candidate set now? Is everyone good? Thumbs up.
If I can just confirm,
Yeah.
The constraints that we're using here, we have match XP. We have the 3 match constraints.
Yeah.
Right. Exactly. And then we have the bin min and bin max and strong start.
Exactly. Yeah. So there's those 6 constraints, the 3 match constraints, bin min, bin max, and strong start.
Excellent. Thank you.
Yeah, great. Thanks for checking. Okay, so once we have all of these constraints set up, we can save our analysis and download and view the Tableau. So this was what Jenny was showing before, where if you click save, you can give it a name. So we can call it like my ditransitives, click OK, and then it'll save a file that you can later load it back into Spot if you ever want to return to this analysis and play around with the settings more. But in addition to that, we can press get results. And now what Spot does is it will display to us all of the candidates that were generated, as well as all the violations that the constraints we chose assigned to these candidates. So if everyone could click Get Results, and then just to make sure we all are looking at the same thing, check that you have all 6 constraints here in the top row. And then also you should have, if you followed along, you should have 33 possible output candidates. So if you've checked that you have the right constraints and the right number of candidates, once you've done that, if you could give a thumbs up. Then when you press Get Results, it also should have created a CSV file. So if you open up that file, can I just get a thumbs up that everyone got a file like this and they can open it in Excel? Okay, I see a few thumbs up. Is everyone okay at this point? Okay, see a few more. Great, yeah, so this goes a little bit beyond what Jenny showed in her talk, but now once we have all the candidates and the corresponding violations, we can put this into OTWorkplace and calculate a typology. So I think everyone has OTWorkplace installed, so you should be able to click in this upper row, the tab that says add-ins. And then you should see this OTWorkplace option. And then you can click Project Start. So just to make sure, I'll walk through that once more. OTWorkplace, Project Start. Click on Project Start. And then you'll want to choose this first option that says New Name. So we're going to make a project and give it a name. And now you can name your project whatever you want. We can just call this ditransitive since we're looking at the ditransitive construction. And then once you type in a name, you press OK. And OTWorkplace will add these labels like input, output, etc., so that it's ready to run the factorial typology. So did everyone get to this point? Can I see some thumbs up for having the project in place? Okay, I see a couple. I'll just wait a second more. Okay, if you didn't get there, feel free to interrupt me and I can go through that again. It was just the project start selection. Now that we have the project started, the next thing we want to do is do OTWorkplace factorial typology. And then we click on fact type calculate. So again, factorial typology, fact type calculate. And then this will basically give us a brief report of like how many harmonically bounded candidates there are and how many possible optima there are in total. Right now we can kind of ignore that and we can just press OK. And then it tells us how many languages we predict to have given this gen and this con. And it tells us that there are 9 possible languages for this system. So now it asks us if we want to name the languages by their outputs. I'm just going to click no. That's not super important right now. And then it asks us if we want to issue the ranking information. So if we did this, it would go through and tell us like, what constraint ranking do we need for a language where this prosodic candidate is the winner, or this one. So for now, once you get to this page, we can click yes. So I'll press yes. And then OTWorkplace is going to cycle through and make those, calculate the ranking for each language. And so I think, again, this is a good place to pause and just ask, was everyone able to create these different rankings?
We can wait a minute here because for me at least it's still generating them. So it might take a second.
Yeah, for sure. Yeah, sometimes it can be a little, depending on your computer, it seems like sometimes it's a little slow. So I'll take a minute. But yeah, once it goes through for you, Paris, maybe if you could let me know, and then I'll ask everyone for a thumbs up on their end too.
If anyone has any questions or problems right now, please feel free to ask.
Yeah, I want to make sure I'm not rushing through this. Okay, seems like another person has it down. Okay, so then what's really cool about this is it tells us all the languages that are predicted to exist given this constraint set and this set of inputs. And not only that, but we can compare this to the typology we saw earlier. So before we saw that Nick Halavoda had identified at least 4 types of languages in their phrasing. So next we can ask, does our typology contain these languages? This might be a little hard to read at first if you're not used to the spot notation, but the curly braces on the outside are intonational phrase boundaries, and then the parentheses are the phonological phrases. So for example, if we look at language 1 here, does this phrasing look like any of the languages in our typology? Sorry, or in the list over here. Does it look like A, B, C, or D? If we look at this language 1 that I've highlighted. Feel free to answer.
Would this be a Zulu-like system?
Exactly, yeah. So this looks like Zulu, right? Because there are no internal phonological phrases. We just have one phonological phrase that contains verb, noun, noun, which is exactly what we get in Zulu. So then we might ask, like, okay, what constraint ranking do we need to generate a Zulu-like language? So what you can do is click on where it says L1, and then it'll take you to this page with a lot more detailed information about what is going on in Zulu. So I think the first thing that's a little interesting to look at is the Hassa diagrams. And so what this tells us is that there are 2 different rankings that will give us a Zulu-like language. So there's one where you have, for example, like match prosody to syntax for the lexical phrases is above bin max and match XP. And also the minimal binarity is really important. It has to be above match XP and match lexical phrase. But it's also possible to come up with a different analysis where, say, what's different about this one? In the second ranking, now strong start is ranked above match XP instead of match prosody to syntax. And so you can start to see the different types of rankings that give rise to different languages. Since we have a little bit of time, I'll also just point out a nice thing about this is it will also tell you, for example, like which candidates you should compare to when you want to figure out like when you want to motivate your constraint ranking. And so this will just give you a lot of useful information about like which candidates favor the winning output and which constraints and which constraints favor the losers. So for example, if we compared this winner and this loser, we'd see that, for example, matching prosody to syntax will favor the winner, while matching all XPs favors the loser. And so by using this information, we can start to get a sense of like what constraint rankings must hold to derive this language. So since we haven't really talked about OTWorkplace too much yet, I'm not going to spend too much time on that, but I will just note there's a lot of rich information we can glean from what OTWorkplace gives us. And we'll talk more about that tomorrow during the workshop. But for now, if we returned to this page, we could say that language 1 looks to be like Zulu. Do we see any, or I guess I'll take a moment to pause and just ask how everyone's doing, if there are any questions so far about the ranking.
Actually, I have one. Okay.
Oh, yeah.
Do you mind going back to the right side of, if we go back to the page of the first language, and you go to the right side, and can you explain how these are ranked and what the lines represent and the relationships are?
Yeah, that's a great question. So the lines basically tell us, like, in this ranking, this constraint, because it's above this one, it needs to be ranked above this constraint. So like, because there's a line going from match PS, a lexical version, above bin max branches, that line tells us that these must be ranked in this order, match above bin max. But on the other hand, strong start in this ranking is not ranked relative to anything else. So that just tells us that if these other relationships hold, then we don't really know or care where strong start is ranked. We'll still get the same output as long as these other rankings hold. Does that clarify?
Yeah, do you mind if I ask a follow-up?
Yeah, for sure.
So those three that you have at the top, you have match, custom PS, bin, min branches, strong start. These are not, so these being the highest on this sort of vertical axis, well, actually, these don't dominate one another, I suppose, because they don't have these lines. That is,
yeah, that's exactly right.
Okay.
Yeah. So since these two, like match, PS, and bin min branches, don't have any lines connecting them, we don't know necessarily where they rank with respect to each other. All we can say for sure is that match PS must be ranked above these other two, and bin min branches must be ranked above the match Syntax-Prosody constraints.
Oh, okay.
Yeah.
Excellent.
And then there are actually multiple possible rankings that could satisfy these conditions. So you could have one ranking where match PS is above bin min and another where bin min is above match PS, but you'd still get the same outcome because their relationship doesn't matter as long as everything else holds. You're going to get the Zulu-like language.
Okay, thank you.
Yeah.